Hi there, welcome to my channel. In this video, I'm going to discuss about the solution for course schedule problem. Let's look at the problem description. There are a total of num courses that we have to take, and each course is labeled from 0 to the num courses minus 1. And also we are given a prerequisites array wherein each entry has a course ID pair. If we want to take the course A, then first we have to take the course B. For example, if we have to take the course 0, we have to take the course 1 first. Okay, and we have to return the ordering of courses that we should take to finish all the courses. If there is no such ordering, then we have to return the empty array. So in the case of example 1, the num courses is 2 and the prerequisites is 1, 0, and the output is 0, 1, because we have to take the course 0 first and then 1. So we have to return 0, 1. And in the case of example 2, the num courses is 4 and the prerequisites has 4 entry, in which we can take the course 1 after taking course 0, and also course 2 can be taken after taking the course 0. So the course 0 will be the first one. And if you want to take the course 3, then 1 needs to be taken first, and also 2. After taking 1 and 2, then only we can take the course 3. Okay, so 0, 1, 2, 3. That is an expected output for this case. And in the example 3, the num courses is 1 and the prerequisites array is empty. So there is only one course. We can just return that one course in the output. The constraints for the problems are the num courses is ranging from 1 to 2000 and the prerequisites array length is ranging from 0 to num courses time num courses minus 1. Okay, and each entry in that prerequisites array is of length 2. The entry in the prerequisites array value are not same, they are unique. Okay, and also all the pairs in that prerequisites array are distinct. Let's look at the approach to solve this problem. So we are given this input where the num courses is 4 and the prerequisites array has 2 entry. So in this, in order to take course 1, we have to take course 0 first, and in order to take course 2, we have to take the course 0 first. So first course we should take is 0 and then 1 and 2. But the number of courses is 4, but there is no reference to end the course 3. That means the course can be 3 can be taken in any order. So the expected output will be 0, 3, 1, 2. So we can model this problem as a directed graph problem. For example, the course 2 and 1 depends on course 0. So this should be taken first. So we put an edge, a directed edge from 0 to 2 and 0 to 1. Okay, based on the prerequisites array. And there is no reference for the course 3 in the prerequisites array, so this will be a separate component in the graph. Okay, so once we model the problem as a graph problem, we can do the breadth first traversal on this graph and generate the output, basically the topological sort order of this graph. So we can use the Kahn's algorithm. First we have to build the adjacency list for this graph, and then we have to compute the integrity of each vertex in the graph. So first for the vertex 0, the neighbors are 1 and 2. So it has 1, 2. And for the vertex 1, there is no neighbors, so it is empty. For vertex 2, there is no neighbor, so it is empty. For vertex 3, there is no neighbor, it is empty. Next we compute the integrity of all the vertices in this graph. Okay, so for the vertex 0, there is no incoming edge, so that's why there is no entry in this integrity map. But for the vertex 1, there is one incoming edge, so the integrity is 1. Same for the vertex 2, so the integrity is 1. And for the vertex 3, there is no incoming edge or outgoing edge, so there is no entry in the integrity. Okay, So once the adjacency list and the in degree is computed, next we have to find all the vertices which have in degree 0 and put them in a queue. So in this case, there is no entry for the vertex 0 and vertex 3. So first we put these two nodes in the queue, and then we start processing. Each time we process the element in the queue, we add that node to the topological sort array, and then we get the neighbors of that node. For example, when we process the node 0, we get the neighbors 1 and 2, and then we decrement the in degree of those neighbors. Okay, so here it is 1 and 1 for both the vertex 1 and 2. So after decrementing, both become 0. So whenever the in degree becomes 0, we have to add that node to the queue. So the 1 and 2 will be added to the queue. We repeat this process until the queue becomes empty. Finally, we check whether the topological sort array length is equal to the total number of cores. If it is equal, then we can return the topological sort array as it is. Otherwise, we have to return empty array because there is some cycle in the graph, so we cannot take all the courses. Let's look at the flowchart. Input for this procedure is num courses and the prerequisites array. And first we initialize the top sort array, and then we check whether the length of the prerequisites array is 0. If so, we can take the course in any order. So we simply return all the numbers in that range from 0 to num courses minus 1 and add it to the topological sort array and return it. Otherwise, so first we initialize the adjacency list and the in degree map, and then we initialize the index I to 0. Then we iterate over the prerequisites array, and for each entry in that array, we read the ID of the first course to be taken and the second course to be taken. Then we build the neighbor list for the first course, and then we increment the in degree count for the second course's ID in the in degree map. We repeat this until all the elements in the prerequisites array are processed. Once that is done, then we initialize the queue which will be used during the traversal. This queue always contains the vertex whose in degree is 0 at that moment. Then for each course ID, we look up the in degree map and check whether there is an entry. If there is no entry, then we add that to the queue. That means it has an in degree 0. Okay, and we repeat that for all the courses. Once the queue is initialized with all the vertices with the in degree 0, then we start traversing the graph. First we check in the outer loop, we check whether the queue is empty. If it is not empty, then we dequeue the first element and then add that to the top sort array. Then we decrement the in degree count of all the neighbors in this inner loop. Okay, so whenever that in degree of the neighbor value is 0, then we add that neighbor to the queue. Otherwise, we go ahead and process the next neighbor. So this will repeat for all the neighbors. Once all the neighbors are processed, then we come back to the outer loop's next iteration and we dequeue the element and add that to the top sort and then get the adjacency list. We repeat this process until this queue becomes empty. Once the queue becomes empty, then we come out and check whether the length of the topological sort array is equal to the total number of cores. Then we can simply return that top sort array. Otherwise, we have to return the empty array. This condition false means there is cycle in the graph, so we cannot take all the courses, so we have to return the empty array. Let's move on to coding. First, I define the constants for the indexes of first and second course in each entry in the prerequisite array. Then in the find order function, I initialize the top sort array with the empty slice of int. Then I check the length of prerequisites array. If it is 0, then there is no dependencies. If so, then I add all the numbers in the range 0 to num courses minus 1 to the top sort array. And return it. Next, I initialize the adjacency list. Then initialize the in-degree map, which is a map of int to int. Next, I write the for loop to iterate over the prerequisites array to build the adjacency list and the in-degree map. I initialize the first variable with the value of the first course to be taken in the current entry, and initialize the second variable with the ID of the second course to be taken. Then I check whether there is an entry in the adjacency list for the ID first. If it doesn't, then I initialize that entry with the empty slice of int. Then I append the ID of the second course as a neighbor of the first course. Then I increment the in-degree count of the second course ID. Next, I initialize the queue. This queue will hold all the vertices whose in-degree count is 0 at that moment. Then I write the for loop to check whether there is an entry exists for each course ID in the in-degree map. If there is no entry for a particular course ID, then I add that course ID to the queue. Then I write the third for loop to process the queue. This loop runs as long as there is an element in the queue. And in each iteration, I dequeue the first element in the queue and then update the queue. Then I add the current element to the top sort array. Then I decrement the in-degree count of all the neighbors of the current element. I traverse all the neighbors and then decrement the in-degree count of those neighbors. And if that after decrementing, if that in-degree count is 0, then I add that neighbor to the queue. Now after processing all the elements, we come out of the outer loop. There I check whether the length of the top sort array is equal to the num courses. If it is not equal to the num courses, then I initialize the top sort with the empty slice. We hit this condition only when there is a cycle in the graph, so we return empty slice, as we cannot take all the courses. Otherwise, finally we return the top sort array we generated during the traversal. Next, I'm going to run the test cases. Oops, there is a compilation error. Okay, there is a typo. Instead of make, I put map. Let me rerun the test case. All the tests passed. Next, I'm going to submit this program. Cool, this program is accepted. Next, I'm going to do the code walkthrough with sample input. Let's do the code walkthrough for this input. The num courses is 4 and the prerequisites array has 2 entries, and the expected output is 0, 3, 1, 2. Okay. First, we initialize the top sort array with an empty slice of int, and then we check whether number of entries in the prerequisites array is 0. In this case, it is not. So we go ahead and initialize the adjacency list and then the in-degree map. Then we build the adjacency list and the in-degree map. So in that, for each entry, we update the adjacency list and then the in-degree count. For example, for the first entry 1, 0, the first course is 0 and the second is initialized with 1. Okay. Then we check whether there is an entry for 0 in the adjacency list, there is no entry, so we initialize with the empty slice of int, and then we append the number 1, which is in the second variable, as a neighbor for the vertex 0. So same way for the second entry we add 2. So the adjacency list for the vertex 0 is 1, 2, their neighbor. Okay, and for the vertex 1 there is no neighbor, so it is empty, and for 2 there is no neighbor, for 3 there is no neighbor. Then as we build the adjacency list, we also update the in degree of the second course. So for example, in the dependency for the first entry there is a 1 incoming edge for the vertex 1, so the in degree is 1. Same way for the vertex 2 there is 1 in degree, 1 incoming edge, so the in degree is 1. And for the vertex 0 there is no incoming edge, so the in degree is 0. For the vertex 3 there is no incoming or outgoing edge, so the in degree is 0. Actually there is no entry added in the in degree map. Then we initialize the queue, which always contains the vertex whose current in degree value is 0. Okay, first for loop we first check the course ID 0 has an entry in the in degree map. There is no entry, so we add that to the queue. And next we check whether there is an entry for the course ID 1 in the in degree. There is 1, so we are not adding that to the queue. Same for the course ID 2. There is an entry, so we are not adding that to queue. But for the course ID 3, there is no entry in the in degree map, so we add it to the queue. So queue now has 0 and 3. Both the vertex have a in degree value 0. Okay. Then we are entering the outer loop. So in the each iteration of the outer loop, we dequeue the first element in the queue and assign that to cur, so which currently has 0. And then we add that to the top sort array. So the top sort array has 0. Then we update the queue. So the queue has 3. Then what we do is in this for loop we decrement the in degree value of all the neighbors of the current node. So the current node is 0. His neighbor is 1 and 2. Both the vertex have in degree value 1. Okay. Then we process each neighbor and decrement their in degree count, and if it becomes 0 then we add that to the queue. So in the 0th iteration we add 1, which is the neighbor of the vertex 0, and in the iteration 1 we add 2, because after decrementing the in degree it becomes 0, so we add that to 2. So when we leave the inner loop we have 3, 1 and 2 in the queue, and the top sort array has 0. Then in the second outer loop iteration we dequeue the node 3 from the queue and then add that to the top sort array. So it has 0, 3, and the queue is updated. So the queue have 1, 2, and the node 3 do not have any neighbor, so we do not enter the inner for loop, and we go ahead and process this next element in the queue is 1. So we dequeue that and assign that to cur and add that to the top sort array 0, 3, 1, and queue is updated. So that now the remaining element is 2, and there is no neighbors for the vertex 1, so we are not entering the inner loop, and we go ahead and process the next element in the queue, which is 2. We dequeue the next element from the queue and assign that to cur and add that to the top logical sort array. So now the top sort array has 0, 3, 1, 2, and the queue is empty after removing the vertex 2. The adjacency list of the vertex 2 is also empty, so we are not entering this inner loop. After processing all the elements in the queue, we come out of the outer loop and then we check whether the length of the top sort array is equal to the total number of codes. So in this case we have 4 elements in the top sort array, and the total number of courses in the input is 4. So we return the top sort array. That is an expected output. Next, I'm going to do the time and space complexity analysis for this solution. Let's do the time complexity analysis for this input. The number of courses is 4 and the prerequisites array has 2 entries. So if we model this as a graph, it has 4 vertices and 2 edges. Okay. So time complexity for this procedure is order of n plus m. Reason is if you look at this procedure, the first for loop iterate over the prerequisites array, it's the list of edges, okay, number of edge, and the second for loop iterate over all the vertices, total number of courses. Okay, so this is m and this is n, and in this third loop, for each node we process from the queue, we visit all its neighbor each time. Okay, for in this case the first loop actually perform 2 iteration, it traverse 2 edges. The second loop perform 4 iteration, and the third outer loop also performs 4 iteration, and the inner loop performs only 2 iteration when during the outer loop iteration 0. Okay, for example, for that node there is 2 neighbors, that's why the inner loop performs 2 iteration. Okay, technically this entire for loop runs m plus n time. For each vertex we visit all its neighbors. Okay, so if we sum all of them, it will be visiting all the edges in the. So if we add the total number of operations, it will be m plus n plus n plus m. It's 2 times m plus n. We can remove the constant out of this, and the time complexity for this procedure is order of n plus m, where n is the number of vertices, m is the number of edge. Space complexity for this solution is also order of m plus n. Basically we are allocating space for adjacency list as well as the in-degree map. The in-degree map maximum size will be equal to the total number of vertices in the graph. For the adjacency list, the space requirement is m plus n, because for each vertices there will be 1 entry in the adjacency list, and each points to all its neighbor. That is equal to the total number of edges in the graph. Okay, for example, for this input, the in-degree map size is 2. Worst case it will be 4. Okay, and the adjacency list space requirement is for each course ID there will be 1 entry, and each of them will in turn points to a list which it is connected to store all its neighbors. Okay, that means the number of edges going out of that particular vertex. So if we add all the space requirements, it will be m plus n. Okay, so the number of vertices and the number of edges, so totally 6 elements. Okay, so if we assume the number of vertices is n and number of edges m, then it will be like n plus m, and we can remove the constant factor and it will be approximately m plus n. The space complexity is order of m plus n. Thanks for watching this video. Have a great day.